This is force and motion due to a spring. We have a spring system drawn, which is pictorially illustrated here, where the force is negative kx, and k is a positive constant. So by Newton's law, F equals minus k of x equals, because force equals mass multiplied by acceleration, which this equals negative kx. So when we divide by k, we'll get this expression here, which is quite common when a common equation what we see in these kind of systems, where our omega is root k over m, and this is the angular frequency. Now we start by guessing a solution. We know that the derivative of sine of t equals cosine of t, and derivative of cosine of t equals negative sine of t. So the second derivative of sine of t equals negative sine of t, and the second derivative of cosine t equals negative cosine t. Now taking a second derivative of the sine and cosine gives the same function back again, but with a minus sign. This is very close to what we need. We now try a function of the form x of t equals c sine omega t plus d cosine omega t, and we take its derivatives again likewise, which we get this negative omega squared x, which is what we had initially. So this does satisfy the equation. And now because the equation of motion is a second order differential equation, the general solution is expected to contain two arbitrary constants c and d. The values of these depend on initial conditions, that is the initial position x of naught and initial velocity x dot of naught. Now to interpret this solution, notice that it can be written in this form here, where a and phi are constants. To see this, we expand the equation above to get this. Then comparing with x of t at the top, we see this equation is valid provided that c equals a minus a sine phi and d equals a cosine phi. To express a in terms of d and c, we add together and square, and then take the square root. So we get a equals the root of c squared plus d squared, because as we know cosine squared plus sine squared equals 1. Now to express phi in terms of a and d, we rearrange the above equation this to obtain our phi plus equals plus minus arctan d over a, where this implies that 0 is greater than c, and phi is bound between 2 pi and 0. Now our constant is greater or equal to constant a is greater or equal to 0, and is the amplitude of the oscillation, which is the magnitude of the maximum displacement from equilibrium. That's when x equals 0. Now phi is called the phase constant. This is related to the time when the oscillator reaches its maximum displacement, according to the equation here. X equals a and t equals minus phi over omega, and at other times differing by a multiple of 2 pi over omega. And the time taken to complete one cycle is the period. This sine has period 2 pi, and omega t equals 2 pi. Now for the equation omega equals root of k over m, our period equals 2 pi over omega, which equals 2 pi multiplied by the root of m over k. The period is now the period of oscillation is reduced if m is reduced. Now if we can add a resistive force to this. By adding a resistive force, we get F equals Fs plus Fr, where Fs is the force of the spring and Fr is the resistive force. The additional force can be written as F of R, our resistive force. So by Newton's law, we get this equation, which we call equation 1. This is the equation of motion for a damped harmonic oscillator. Now this time we guess that we have an exponential decay term, and we again likewise we take the derivatives, first and second derivative, and we substitute into equation 1, which is this, and collecting terms in sine omega t and cosine omega t gives this. Now this equation must be satisfied for all t, so divided by we divide in both sides by the exponential of negative lambda t, and that gives us this. Now this is the equation. This is an equation of the form given here, where c and d are independent of t, which is satisfied only if the coefficients of sine omega t and cosine omega t are 0. These determine the two uniform coefficients of omega, lambda and omega, in terms of the coefficients of the differential equation. I forgot what you call this now, the Greek letter. We'll just call it y for now. M, y, and k. The second equation gives lambda equals y over 2m. We substitute this into the first equation to get this. So the required solution is here, where our omega equals this, which is not meaningful when y is sufficiently large that y squared is greater than 4km. When y goes to 0, we recover the undamped oscillation. And that's force and motion due to a spring. Please like and subscribe.